universality that they possess, which I will explain. So ask this question: how common are weak values outside the spectrum? You know, you have an operator, you have its eigenvalues, and you have your pre- and post-selected states. So if you have, because the ensemble of all pre- and post-selected states which live on their two Hilbert spaces, you could then ask, in that ensemble, how common is it for the weak value to be outside the spectrum? And that's what I'll calculate first of all. This is work with Pragya Shukla. I mentioned her yesterday. We have several papers together. And so the weak value is, remember, the real part, and I'm considering the real part today, of the matrix element of your operator that you're measuring between the pre- and post-selected states divided by their overlap. So call that, just denote that simply by A. And the probability that you'll get the value A is, as always with probabilities, the average of a delta function of A minus the expression for A. Here it is. And what is the average over all random, over a whole ensemble of pre- and post-selected states? So I'm thinking you've got n eigenvalues between some range, and it's finite, of course, otherwise there's no meaning to super weak, it has to be outside the range. And then the superoscillation probability would be the integral of this probability of the value A outside the range, from minus infinity to minus A max to plus infinity. Okay. Well, you expand the states in terms of the eigenstates of what you're measuring. And here they are, the eigenvalues are the ANs, and the eigenvectors are the alpha n's, and there are n of them. Okay. So you can expand the states, and you have coefficients psi n and phi n. These were the overlaps n phi and n psi that we discussed yesterday. I'm just using a different notation, forgive me for that. So here's the weak value now expressed that way, and these little quantities here, yesterday what I called capital C n, and I'm sorry I didn't use the same notation when preparing for these talks. I should have done, doesn't matter. Okay. And these are complex numbers, these products. So call them B, which has a real part and imaginary part. Okay, these are two separate aspects. And okay, so here's the probability. It's the average of a delta function over these BNs, BN1, BN2. These refer to the products of the two states of the delta function of the A that you're seeking minus the general expression for the weak value. Okay. Now, in many computations with delta functions, you write the delta function as its integral representation, and that brings the thing you're averaging up into the exponent, which is often simpler. Now, a problem that arises here is that you've got this denominator. This is central to weak values, but it makes the averaging awkward. And so there's a trick that you use to deal with that, which is in a way, the centerpiece of what makes this kind of calculation different from other calculations involving involving ensembles. Gaussian comes in a minute. Now, you have this sum over the BNs, and I'm calling this awkward denominator, and I'm calling that C. It too has its real imaginary parts. Now, I want to interpret that denominator as a constraint implemented by a double delta function for these two C's, and that would bring this up into the numerator as well. So here we are. You've got now lots and lots of integrals. The integral S, which is over the delta function, the integral representation of the delta function itself, and then I've got integrals which will give you the delta functions for the C's. Here they are, the T1 and T2. And also, of course, I have to integrate over the C1 and C2 themselves. Yes?
So the question, the first one question I have, you have pre and post-selected phi and psi functions.
Yes, independent of each other.
And you are randomly distributing them uniformly
Yes.
on a sphere, on two spheres.
On
I
a
assume.
big sphere. I mean, actually, it won't be necessary to include that sphere explicitly, but yes, that's what's really happening.
But it's on a finite space, compact space.
Yeah, but n big, the n is large, by the way. Excuse me, n is large. You'll see in a moment.
Well, I was referring to this only because of the well-known mathematical fact that a uniform distribution on infinite interval makes no sense. I assuming you are not
No,
going
no,
to fall into this
of course
trap.
not. These live on their sphere.
Okay.
But,
And the second one, it looks
we
like...
won't need that information, but it's correct what you say. Second?
Second is that you are really not distributing separately phi and psi. You're only looking at the real imaginary part of their scalar product.
Well, that's all that comes into this. It's all that
But
appears.
is that equivalent?
You'll see now. Wait. Okay. And remember, I defined these things as B's, exactly these products, and the real imaginary parts, of course, independent of each other. I mean, they're completely separate. Now, here's the point. N is large. We're using the central limit theorem, and these sums, irrespective of what their distribution is within reason, are Gaussian random variables. Fundamental. Okay. That makes everything possible. We'll see a case in a little while where we can't do that, but for the moment we can. Right. And now we use the beautiful familiar result that the average of the exponential of something, if it's something is a Gaussian random variable, is e to the minus half its variance. So you do that, you have this quantity here that you're taking the average of, and one thing you need, that these objects, these products, have a common variance. There's no difference between the real part and the imaginary part in these products. They have a common variance, and in terms of that common variance, the result you get involves the variance of the eigenvalues within their range, which is the one parameter that survives in this theory, as you'll see in a moment. And this is using the theorem, e to the minus a half of the fact that they're also independent from each other. Now, a very nice thing you can do, you can now scale away the B, that's the variance of these little products, and you can scale away the N, which is the number of eigenvalues that you have. And the result is something which is universal. It's an integral that you can then work out. And I won't go through it, but it's an integral that's straightforward. Here's the A that you're seeking the distribution of, and here's the one parameter that remains. And so here's the result. It's a Cauchy distribution. The weak value probability is 1 over, well, basically 1 over A squared to the 3 halves, normalized in this way. Of course, it comes out naturally normalized by the way you've done the calculation. And so the super weak probability, which is the integral of this outside the range of the spectrum, is 1 minus something, and here it is. Now, A max is the range over which the spectrum exists, and the average value of A squared is tells you how they're distributed within that range. And that doesn't matter very much, but I'll show you 3 examples. You can have a uniform distribution, in which case the super weak probability is about 0.13. You can have a random matrix, a semicircle distribution, in which case the random probability is 1.10. Or you can have something concentrated near the ends, in which case this is as big as it can be, and it's 0.3. So even from this, you see that weak values, super weak values, are not so rare at all. They're not e to the minus n or something, which you might have expected. Of course, as we know from superoscillations, if you want to get a lot of superoscillations together in a small region, that's hard to get. You work hard. But still, modest super oscillations, and you don't specify how big they are, giving a super weak value for super weak value for the weak value of the thing you're measuring, are actually rather common. We'll see much more of this now. Now, of course, this is the theory, so it's good to test it. Now, you can test it with simulations, 10, 100,000 samples with random B's, and all these A's lying within the range -1 to 1. Taken from a uniform distribution. I tested that bit of the theory. Here, n is 100, n is 5. You can barely see the deviations. If you take the logarithm, you see the superweak regions are shaded. These are the regions outside the spectrum. I forgot to make this pointer bigger. Let me do that now so you can see more clearly what I'm showing you. It's better to just allow me to do this. Just a moment. We were having such a nice discussion before that I forgot to prepare. There we are. Good. So here we are. But if you take the logarithm and you see in the tails, then you see some deviations. But n equals 100, even n equals 5, it agrees very well. So the theory is right, no doubt about it. And even 5 is enough for things to be approximately Gaussian enough for this model to work.
This is the integrated probability, right?
No, it is the probability density. It's P of A. It's P of A, and the integral outside the region, these tails, that's the superweak probability that I showed you a moment ago. So for this particular case, it's about 0.1 something. Yes. Okay, so this is how you do that calculation, and it's a nice result because it's universal. It doesn't depend on anything except the statistics of how the eigenvalues are distributed within their range. Good. A distribution is different if the states are real. If you have time reversal symmetry, that depends on the physics of what you're doing. But if they're real, it's a little bit different. Still universal. Instead of the 3/2 power, you've got the 1 power, and there's the superweak probability as a slightly different form. But so you go through exactly the same calculation. A little bit simpler actually for the real case. You've got half as many integrals, but still you can calculate it. And in particular, if you have all of the eigenvalues scrunched up near the ends, the superweak probability in this real case, time reversal symmetry, is a half, very strong probability of being outside the spectrum. Now this is very different from the distribution of conventional ordinary expectation values, not weak values, where psi and phi are the same. And that's very different, not universal at all. Indeed, here it is. It's a much more elementary calculation. It's e to the minus, it's exponentially small, because it means that the probability of getting A is much stronger if A is in the middle of the range, what you expect. Of course, this doesn't apply outside the range, in fact, because there's 0 probability there, but then this Gaussian has become very small. Remember, we're thinking n is large. So completely different result. I mean, just a totally different type of distribution, and not universal in the sense that it involves the n, the number of eigenvalues. Very different if you've got spin half. Then you've only got 2 states, and of course you can't use the central limit theorem there. But what you can then do, and this is work with, again, Pragya Shukla, Mark Dennis, and his student Ben McRoberts, what you can do there is you explicitly integrate the psi and the phi over their sphere. I mean, you don't need any statistics, you actually do the integral over the block sphere of the spin half states. There's a fun integral to do, but I don't want to speak about it. It's in the paper. And there's the distribution. See, this is the one we just had, the dashed one. But here's the distribution that you get. And the superweak probability is 1/3. Now, this enables you, knowing this distribution, and I don't think I've written the, I haven't written the formula for it, but I can't remember what the tail is. I think it's the same as the tail we had for the universal one. But here we can complete a story which started in 1988. You see, one of the first papers, I think the first published paper on weak measurement by Yakir and David Albert and Lev Weidman had this wonderful title: How the result of a measurement of a component of the spin of a spin half particle can turn out to be 100. Well, now we can work out the probability of that. Imagine that you do this experiment and you randomly choose the pre and post selected states. What's the probability that you will actually get the result that the spin is greater than 100? Well, the answer is it's 120,000th. It's the exact result. So that's a sort of fun completion of the story that Yakir and his colleagues started in this respect. Okay, so that's the probability. Now,
but that's an inequality. Do you
what?
have the same result as inequality?
What?
This is for greater than 100.
Yeah, yeah.
But they ask for exactly 100.
No, I know. But but they didn't ask for the probability. They just showed that you could do it, of course, which of course you can. No. I mean, the probability of exactly a half is 0, of course. Exactly 100 is 0, but they can make states that do it. Of course you can, which they did. This is a sort of prototype calculation of a number of different statistics, which I'll now just tell you. So waves, superoscillations in waves. So Mark Dennis and his colleagues wrote a paper which actually was the first calculation of this kind. And the one I showed you, this most general one with Pragya Shukla, wasn't the first one, it was Mark. So we considered waves, he considered waves, and in the plane, speckle patterns, and then he and I generalized this to d dimensions. So here's the problem. You've got a wave, I've often shown you this, you've got wave in d dimensions with its modulus and its phase. And you have the local wave number, which is the length of the local wave vector. I should have put modulus signs here, which I didn't do. Monochromatic waves, so band limited, okay? And the superoscillations are where this length, as a function of position, is greater than the wave number of any waves in the superposition. I've said this many times. Now we're considering random waves. In other words, we're considering the sum of many plane waves going in different directions. And again, from the central limit theorem, these are Gaussian random waves. And we seek the probability that if you look at a particular point, the probability that that point you've chosen, the local wave vector will be superoscillatory, larger than the wave vector of any of the plane waves, which of course is the integral from k0 to infinity outside the band-limited range of the probability distribution of these local weak values of momentum, as we now call them. Okay. Well, we can do that calculation. The techniques are rather similar to what I've just shown you, so I don't want to go through writing all those integrals again, anyway, in the paper. So I'll just show you. So here's a random wave. I have 10 plane waves, phases color-coded. This is one square wavelength, illustrating the interesting non-trivial behavior on the wave sub-wavelength scale. Here are the vortices, and these lines are the, which I haven't put arrows on, are the lines of the local wave vector. Now here, I've blocked out the region that's not superoscillatory. So the bright region is superoscillatory. Of course, it includes the vortices, where close to which the local wave number goes to infinity. But it's much bigger than that, and it's actually substantial. Okay, now we did this Gaussian random function calculation for d dimensions, and here's the result. Here's the probability, and you can look at this distribution for different values of the dimension, and then you can calculate the super weak probability, super oscillation probability, which is the integral from k0 to infinity. And there it is. Depends on the dimension, but not much actually. Goes from about 0.3 to about 0.4. In 2 dimensions it's 0.3, and that's the pioneering calculation that Mark Dennis did. But it's not that different in the general case. A little bit more. You'll be a little bit more careful. But so, once again, these superoscillatory, super weak things are rather common. Okay, they're not at all rare, exotic beasts. Now here's another example. Imagine you've got a 2-dimensional problem, waves propagating in different directions, x and, what have I called it, z, all of which have a z component of momentum which is positive. So all the plane waves are moving forwards, okay? However, the local wave vector can have a z component which is negative. This is backflow or retropropagation. There's some discussion of this in quantum mechanics literature. It's a phenomenon called backflow. Gonzalo Muga has drawn attention to it some years ago. Anyway, here you are. Here's the ensemble. You've got plane waves, each of which have a positive z component. And all of these components, the x components, which I'm calling kn, are of course less than k0, 2 for 2 dimensions. So this is the ensemble, and you do the calculation. As I say, backflow, negative kinetic energy, optical retropropagation. So here's a picture of 21 waves propagating in directions uniformly distributed between minus pi over 2 and plus pi over 2, all going forwards. And I've shaded the retropropagating regions in x and z, a little bit smaller, about 4% for this particular problem, 1 minus 2 root 2 over pi. You can do it exactly. So this is a rather curious phenomenon. If you have, as very commonly in experiments, in speckle patterns, for example, a rather narrow distribution of angles paraxially, in fact only going over a range minus theta max to theta max, then the retro probability is actually theta max over 180. Yes, press your thing. Press your, yes.
Which of the localized k value or k functions are you using? You talked about 5 different ones.
About
which of the localized k formulations are you using, k of r, to get these backflows?
Oh, I'm just taking the local phase gradient of the total wave, and I'm looking at the z component of it, and I'm asking when is that negative, right? Okay, so there it is. Or you could consider relativistic waves satisfying the Klein-Gordon or the Dirac wave equations, and you can have a wave where the spectrum of plane waves, each of them is has a subluminal group velocity, but there are some points in space-time where the group velocity is superluminal. I want to show you how that works. I wrote about that a few years ago. Klein-Gordon waves. So here's the Klein-Gordon equation. The mass is 1, c is 1. There we are. And there's a dispersion relation which comes from there. Omega of k is the square root of k squared plus 1. Now, the group velocity operator, what is group velocity? It's the gradient of the Hamiltonian with respect to momentum, which is the omega by dk operator. There it is. So that's the group velocity operator in terms of the momentum operator. So you can superpose waves with subluminal group velocities u. So you can specify an ensemble of u's, all of which are less than 1. C is 1. Okay. Modulus of less. Going in one dimension now. All of which are between minus 1 and 1. And the correct, so kx minus omega t, when you write it in terms of u, becomes this. So that's the ensemble of subluminally propagating exact solutions of Klein-Gordon. And the weak value, which is the local group velocity, the weak value of the group velocity in the conventional way, is simply the expectation value of this u here divided by the wave itself. This is, remember, we're pre-selecting this wave, this state, post-selecting position. Okay, at some given time, doesn't matter. So super weak means superluminal in this case. So for some space-time points, this quantity can be greater than 1. Here's an example where I've just chosen to give an instant, and I've made a simulation, and I've looked at this local group velocity, and it's between minus 1 and 1 for most of the positions, but not all, and you get sometimes greater than 1, sometimes less than minus 1. Here's a space-time simulation, the space-time simulation. These rather curiously shaped places are regions where the local group velocity is greater than 1. I don't know how you'd measure this. It's, of course, just to demystify, I mean, we're not talking about sending signals faster than light. That's nonsense. You can't do that. We're just talking about places where this operator, it's a good self-adjoint operator, so in principle you could measure it. I don't know how, maybe you've got some ideas, where this would be greater than C. And there's a theory, I don't want to go into the details of it, but it depends on the variance and the mean of the distribution of group velocities in the range -1 to 1. A little graph here depends on these two parameters. And it's always less than or equal to a half. Okay, so that's another example.
Is the randomness due to the simulation because you...
No, the randomness means, I'm averaging over the randomness, and here's the randomness. It's this superposition of complex coefficients. So it's a Gaussian random function if n is large enough.
But you uniformly distributed A sub n's.
No, it doesn't matter. I mean, it doesn't, because of the Gaussian randomness, that eliminates lots of detail, and all that remains are the mean and the variance of the distribution of subluminal group velocities within the range.
And after you average, you still get this irregular pattern.
No,
right?
no, that's an exact simulation. That's not an average.
Oh, okay.
Sorry.
No, I understand.
Excuse me, I'm sorry. I should have said. No, that's for just to show you what happens. This is a single instantiation of this thing, just to give you a picture of what really happens. Okay, so now the Dirac equation. Well, here's the Dirac equation in one dimension. It's only, in one dimension, as is well known. The Dirac equation is a 2x2 equation, two-component equation. It involves the Pauli matrices, and the velocity operator, d Hamiltonian by dk, is just sigma 3. And the eigenvalues are plus and minus 1. That's the well-known Zitterbewegung. You know, the expectation value of the velocity of a speed is always plus c or minus c, and as we know. But that's not true of the group velocity if you pre-select. So we're pre-selecting with some state. Here it is, and it has. Now, just a second. Oh, it has two components. That's right, two components. They're related by the Dirac equation, and here they are. This is the same as before, except now it's a solution of the plane waves corresponding to the Dirac equation. Two components related to each other. Here they are, given group velocity, and here's the amplitude of that component. And there are again many of them. Okay. So post-select with position, but you've and you also have to post-select with your initial spinner, which involves some angle theta, as always with theta and phi, as always with spinners, of course. This is a general form for the spinners. Now, the weak value would depend on how you pre-select and on where you look. And the local, it's again the local group velocity, which you can write as an operator. And you can get the super weak probability by averaging over theta and phi and the distribution of the group velocities. You've now got a little bit more work to do. And actually it's always between 0.3 and 1/3, remarkably narrow range of, depending on the distributions that you choose. Now here's some Dirac simulations. I've shaded the superluminal regions, and again, where you go outside the range between -1 and 1. I've chosen a particular sample with those coefficients. I can't remember how many of them, 10 or 100, I don't remember how many that we chose, and just calculated the local group velocity. Or you can look in space-time. Now, there's probably a lot to understand about the topology of these regions of superluminality and why they're different for the Klein-Gordon equation and for the Dirac equation, and I haven't explored enough to know how common these particular wiggly weird shapes are. In the case of the Dirac, of course, this is a particular choice of the spinner that I have for each of the with which I post-select. So there's probably a lot to be understood here, which goes beyond what I'm telling you now, which I haven't explored. But anyway, this is how it is. Oh yes. Now, I want to tell you a rather curious little tale. Some of you have heard it before. to do with combining both the two-state idea and the relativistic idea. You will remember, a few years ago, there was this claim that neutrinos had been observed moving faster than light. Okay. Now, most of us, me included, guessed that it was some mistake, and it turned out to be. But while it was uncertain, it was worth thinking about how it could possibly make sense without overturning the whole of physics. And Pragya Shukla called me and on Skype and said, could this possibly be the result of a weak measurement? Now, of course, my colleague is Sandu Popescu, and he had Nicolas Brunner, who had, as his postdoc, who had worked with Nicolas Gisin, is now back working with Nicolas Gisin in Geneva. And so we wrote a paper about this. And we summarized the result, as is customary to do, in the abstract, which just simply read, probably not. This caused me a lot of trouble, actually. I spent a week delayed arguing with the chief public editor of the Institute of Physics, and said, no, you can't have an abstract like that. People won't know what it means. I said, they will know what it means. Well, how will people make sense of it if they look at one of the abstracting journals? I said, but they'll see it in conjunction with the title. It's a very carefully chosen abstract. If I just said no, it would have not really included the fact that you have to do a calculation in order to know that it's no. Anyway, finally, I had to promise I would never do such a thing to her again. And this, to my surprise, this went viral. It was picked up by a German daily newspaper, and I got these emails from people in Germany saying, oh, what a wonderful abstract it is. It's not my favorite abstract. My favorite abstract is in a paper on geometric phases for fermions by Barry Simon, Yossi Evron, and someone else. 1989, Communication of Mathematical Physics. Abstract. Yes, but some parts are reasonably concrete. That's my favorite, not mine. Anyway, what is this all about? It's about this. There's an analogy between neutrinos, excuse me. I'm honored yesterday, of course, with the prize, and polarization. It's as though space is birefringent. And there are two neutrino flavors. There are more than two, but two relevant to this. Call them mu and tau. They are. And these are superpositions of mass eigenstates. And the initial state, coming out of this beam that they had, is the state mu, which is a combination of the plus and minus. And there's some wave packet envelope traveling along with the mean momentum to start with. And there's this mixing angle that corresponds to mu-ness. Okay. Right. Now, these evolve, they've got different energies because they've got different masses. And they have subluminal group velocities, and this distorts the wave arriving at the detector. This was the idea. And it can distort it in such a way that if you post-select a certain state, in fact they post-selected mu, the same state, it's no longer mu once it's evolved because each of the parts have evolved differently, and it could generate a mean position corresponding to a superluminal arrival. That was the idea. And it's a correct idea. It conceivably could happen. I'll show you. The effective velocity shift is the weak value of the velocity difference operator. Well, here it is. Now, what does that mean? This is the difference of the two group velocities. By the way, the group velocities themselves, less than c, are not known, but the difference is known. And the group velocities themselves involve the mean plus the minus the difference. And that is, they are both subluminal, of course. I mean, the most one could be exactly c, but probably not. And this will give you an effective velocity shift, which you calculate. You do the calculation using the standard weak value formalism. You could do it barehandedly. As with all these weak value calculations, you could do them without knowing about weak values, but it's very helpful to have that picture. It unifies many things. I just want to make a comment. I should have said, the good thing about having Nicolas Brunner in the collaboration was that he, 10 years before, had written a paper with Nicolas Gisin where they had done experiments in optical fibers with polarization where they actually did demonstrate superluminal group velocity exactly according to this scheme. it again doesn't mean they can send signals. It means that the pulse reshapes itself so bits of it catch up with other bits. The front never moves faster than C, of course. So this is just that's common to all the superluminalities that now begin to come in different areas of wave physics. Okay, now, so the point is that this object added to the mean can exceed C, provided these quantities here are appropriately chosen. Delta E is the difference of energies, mc squareds, of the two neutrino eigenstates. So this is a possible amplification factor, amplifying this difference of the two group velocities. And here's how it might happen. Here's a picture, greatly exaggerated. So here are two separate Gaussians, say Gaussian, it doesn't matter, which have arrived slightly differently, and they're almost would be in antiphase. I've drawn the modulus here just for simplicity. So then what's the sum of them? It's something very small. Again, almost near destructive interference that comes when you have these weak values. But its mean, it's not a Gaussian shape anymore, but its mean, here it is shifted. It shifted away from the maxima of the two Gaussians. And this is a special case of what we talked about yesterday, which is supershift for n equals 2, a kind of weak supershift, but still it can happen. Well, did it happen? Then you need a calculation. They claimed that the delta V that they'd measured, the delta V of the neutrinos is about 10 to the minus 24 C. That's known from measurements on neutrinos. But what they claimed, moving faster than the speed of light, was a difference which was about 10 to the minus 5 C, enormously larger. Well, you therefore need the amplification factor to be 10 to the 19. And there's no way, looking at any of those numbers, that could happen, especially one of the quantities that appears there is 0.03, it needs to be nearly 1, and so on. Now that's why we said probably not. Okay, 10 to the 19, too many orders of magnitude for this little miserable effect to conceivably work. Still, it was fun. Okay. The fun thing I'm going to tell you, I didn't quite know where to put this in this series of lectures, I want to describe some really beautiful work not by my colleague Mark Dennis and his postdoc Jörg Goethe. And it's a beautiful example of how weak values can be a unifying concept in explaining rather complicated things. And this is the following. They wrote two papers on optical beam shifts as being analogous to quantum weak measurements. Now, there was a precursor of this, Hoston and Kwiat, a much quoted experiment, but the theory that Mark and Jörg gave following that is much more extensive, and I want to tell you about it. That will be the end of today. So you have light incident on an interface between two media, the different refractive indices. Real refractive indices, the non-Hermitian case is different again. And you have a beam where you specify the polarization and you specify the angular width. And this is a cartoon of this virtual reflected wave that you would have naively. Now, what you measure is this beam that comes out, and you measure its polarization. In the language we've been using, the operator you're measuring is the polarization state, and the pointer coordinate is the shift in the centroid of the reflected beam, because it's known that the beam doesn't come out where you think it should come when you have interface between two media. In the calculation, the only quantities you need are the Fresnel reflection coefficients for the in-plane polarization and the outer-plane polarization as a function of the angle of incidence and reflection. So these are known quantities from Maxwell's equations. Okay, so the pointer coordinate is the centroid of the reflected beam. It's convenient to draw it as a virtual beam, but actually it comes from someplace here, and that's the shift that's measured. The in-plane shift is the Goose-Henson shift, that's what it's called, and the out-of-plane shift is called the Imbert-Fedorov shift. So this beam is shifted in the same plane and also out of the plane. Hoston and Kwiat measured the Goose-Henson shift. Now, the beauty of this, the pointer coordinate is two-dimensional, okay? So it's a little vector. More than that, the momentum shift, the imaginary part of the weak value, is the fact that the beam doesn't quite come out in the direction you think it would come out. It has a direction dependent, it comes out slightly the wrong direction, which again could be in the plane and out of the plane. So there are 4 different shifts, and they're all unified by this notion of weak value, which they discuss in great detail. And they need certain matrices, they need, sorry, yes, here's the formula. 2-dimensional shifts as weak values, which can be complex, giving you the position shift, 2 dimensions, and the angle shift in 2 dimensions. And these involve certain operators, R0, R Goose-Henson, and R Imbert-Fedorov. It doesn't matter, but these depend on these Fresnel reflection coefficients. And they have this beautiful, huge table showing how the weak measurement encompasses all possible shifts that you can get with all different combinations of the incident polarization and the final one that you choose to measure, which is the post-selection. Very interesting combination of then all these quantities here. For the position shifts, you take the quantities here which are real, multiply them by 1/k, it's a detail. For the angle shifts, which are the ones that are imaginary, you multiply by the square of the angular width of your incident beam. These are all very narrow incident beams. And these quantities, they define them in great detail in terms of the Fresnel reflection coefficients. I don't want to go into details of this, indeed I don't remember all the details, but I just want to point out this is a very beautiful example of where the notion of weak measurement unifies a huge variety of phenomena. Some of them have been measured, not all of them have been measured. And this is in classical Maxwell optics, but very subtle. People were, the literature is a real mess about the different types of shifts you get if you use different types of polarization, and whether your incident, if the second refractive index is smaller than the first, whether your incident before or after the critical angle and so on, but all becomes clear in what they do. I think that's enough for today, okay? And so statistics and neutrinos faster than light, not, and sorry, and this lovely example of the beam shifts, okay? And tomorrow, this is the last of those lectures, these lectures in the afternoon, and I shall leave immediately afterwards for the airport. Tomorrow I will talk about, in some detail, about what you can and can't do with superoscillation for seeing small things. This superoscillation and super resolution, which I've touched on in a number of talks so far, but there's some details I want to tell you about tomorrow, and there's some lovely, rather subtle mathematics, which I think could be explored more. So that's tomorrow. Okay. Good. Good. So?
The question I have, you mentioned, just trying to make sure that I understand.
Yeah.
You said that the local wave number is coming from a Hermitian matrix, so it's always real, right? You said that?
I'm defining it. I mean, of course, you can talk about the local gradient of intensity, and that would be the imaginary part of the weak value. I didn't speak about that, but yes, I spoke about this real gradient of phase. That's a real thing.
It's a real thing. So
real vector.
The only problem is it could be superluminal, and then
superluminal, or it could flow
backflow,
backwards, or it could be greater than k. There are different cases I've looked at.
So what would it take for maybe the choice of the pre-selected and post-selected states to guarantee there are no backflows or anything funny going on? Or it's a difficult
plane wave is
theorem
one plane wave is one example, of course.
No, I know example. I'm talking about the general
not
statement.
trivial, because Well, that's an example. I mean, I showed you in the first lecture, if you have simple two-plane waves, strength 1 and strength A less than 1, and then there are regions of with the two wave vectors of length 1. Okay, but still in the interference, you can find places where where it's superluminous. So even with two-plane waves, you can't avoid super oscillatory. So it's actually a good question. It could well be that you can't avoid, unless you have one plane wave. It's a good question. Can you concoct a non-trivial wave which has nowhere, even in one dimension, let's think, nowhere will be super oscillatory? I suspect you can't. Good question. To think about it.
You can, you say?
I think you can't, yeah.
Oh,
cannot. Mm-hmm. I mean, just as this little example with two plane waves, you always have regions where it's super oscillatory. You know. Yeah, thank you. Good question. Yeah. Hmm? Okay. Thank you. Now tomorrow's lunchtime lecture is not here, is it? It's somewhere else.
No, it's here.
Because on the program, on the advert, it's something called 119 or something different from here.
Okay. Yeah, it's here.
Oh, it is here.